5. Okay, so today we're going to go over 3 problems. I don't know if you had a chance to look at the midterm review session notes. So there's several documents to try to help you figure out what's useful information to absorb for the midterm. There's the midterm review session, which we'll be going over today, which includes 3 problems. There's the midterm practice problems, which includes 5 problems. So we'll be going over 2 of those from that. And then 1 from today we'll be going over 2 problems from the midterm practice problems document, plus an extra one about externalities. The midterm practice problems, those set of 5 problems, are posted in the course files along with their solutions that are pretty well written up. So you can, if anything today confuses you, you can go look at the solutions there too. I'm going to post this recording afterwards. And there's also the midterm practice questions that Meredith posted in the midterm, the practice midterm, here we go, from last year. The practice midterm is a little bit different than this year's midterm just because every year Meredith updates the course. And that's why the practice midterm, some people were asking on the discussions, like this question is a little confusing because we didn't cover it in class. The course content from last year was a little different because every year Meredith tries to make it the most relevant to whatever's going on in the electricity market. So just a note on that. Okay, so why don't we jump on in? So the first problem in the midterm review session is about externalities and optimal taxation. And so this is sort of at the heart of the things that we're talking about in this class is when you have an externality like pollution, how do you create an efficient outcome using a particular type of policy instrument? The tax is a type of policy instrument we're talking about. So in this problem, the setup is that we've got market demand. That's 200 minus Q, where big Q is the market supply quantity. We have the total costs of the industry, all of the firms in the industry, is 20 plus Q squared. So this is total costs across the whole industry. We're going to assume that these producers are all price taking and competitive. And so we can use the marginal cost curve that we can derive from this directly as the supply. And there are some damages equal to 5 plus 1/2 Q squared. So whenever the firm outputs their good, they're also making some sort of pollution or externality that is related to their output. So I'm going to mark this with damages. Damages, just to be very clear. So the first question is, how do we find the socially optimal level of production? If we could just force the firm to produce at some level called command and control, what level of Q would we choose to make the socially optimal outcome where marginal benefits equal marginal costs? So the heart of this problem, we could start with the welfare function and then take the derivative of it. But what you end up getting for the socially optimal outcome is just marginal benefits equals marginal costs. So let's go ahead and start there. So the marginal benefit in this situation, the marginal benefit of the output is going to be the consumer purchasing the good. The last consumer to purchase the good is ambivalent between their choice. So their utility that they're getting from purchasing this is going to be equal to P. So we know the marginal benefit is equal to P. And the marginal cost is going to be the derivative of our costs. So we're going to have total costs plus our damage function. I'm going to put this is P, the damage, the demand curve. So if I plug in the demand curve over on the left, we've got 200 minus Q equals 2Q, which is the derivative of the total cost, plus Q, which is the derivative of the damage function. I'll write that up here. Marginal cost equals 2Q, and marginal damage equals Q. So that equals 3Q. And when we add that over, that means we've got 200 on the left and 4Q on the right. So Q star is going to equal 50. So this is what the socially optimal outcome would be. Yeah.
I get like
Yeah. So what we could do is on the left-hand side for total benefits is we could be thinking about the producer and consumer surplus. But when you're thinking about at the margin, like after you take the derivative, the consumer surplus is the integral under the demand curve from 0 up to where the quantity you're producing at, right? So then when you take the derivative of that, the derivative of an integral, I'm not saying this very well, the derivative, if we go from 0 to Q star of P of Q, if you take the derivative of that with respect to Q, then the fundamental theorem of calculus tells us that's just equal to the function evaluated at Q star. Yeah, so there's like some math and integration that goes behind this, but I think what we want to be thinking about is marginal benefits equals marginal cost, and that the marginal benefits in this case are the price. So now we've got our Q star. Our Q star is the socially optimal output. The second question is, what tax would we want to use to address this problem? So let me scroll down here. Part B is some tax T. We want a tax to get Q star of equal to 50. Because we want to be providing an incentive that aligns the firm's marginal incentives with the social incentives that make up our social optimum. So if we write down the profit maximizing condition of the firm, if the firm is under a tax, then we can say, instead of command and control, we're going to apply a tax. In the first part, we are forcing the firm to output at some level Q. So we could choose Q directly. This time, as a policymaker, we're choosing T, the level of tax, so that the firm will choose Q that we want. So now we need to write down the firm's first order conditions. So we start with pi, which is just P Q times little q. So remember, this is a lot of firms in the industry. So we're going to be thinking about little q, and each individual firm doesn't have the ability to affect big Q because they see themselves as some like very tiny firm. So they're going to assume that the only thing they control is their little q. And then minus their costs, which would be 1 over Q total costs. Because if we look up here, this is the industry-wide. Industry-wide total costs. Oh, sorry, not over Q. That'd be over N. And if we wanted to substitute Q equals N times little q, and then the total, I'll put in the total costs. And then the quantity, so the price, the demand function is 200 minus NQ times Q minus 1 over N times 20 minus 1 over n times q squared. So then the first order condition, this is just the profit function. So the actual FOC is going to be the derivative with respect to little q. And let's see, we've got 200 minus 2n q minus 2 over n. Oh, I see. Q squared. So here again, I'm going to say that n equals nq. Where big N is the number of firms. So then we get 200 minus 2nq minus 2nq. Oh, sorry. 2n little q over n. Okay. So now we can set that equal to 0. This is the first order condition. So let me rewrite this bottom part. This equals 200 minus 2. Here, right, minus q times 2n minus 2. So then we've got q equals, oh, I forgot to subtract the tax in here. My apologies. Let me write this in purple. So the total costs for the firm, I skipped this part. This is the profit. This is the total revenue. This is the total cost. And then we also have to add the tax burden. So this is going to be subtract t times little q. This is a very important part, so apologies that I missed it. This is the whole point of this exercise. If we want to find the tax that forces the profit, the firm to choose little q so that they are picking the optimal little q. So if we add that back in here, this is TQ minus TQ. When we do the derivative, that's minus T minus T. Okay. And we've got minus T equals 0, minus T equals 0. So then now we've got 200 minus T over 2n minus 2. Okay. Yeah. Oh, yes. Sorry, I was doing some fast math and moving this over to the right-hand side. So I added that term over to the right, and then I divided by the 2n minus 2. Is that?
Just this term like in the middle for n plus 2, so that one is like.
Oh, from earlier? Or?
No, like there, but the one that you circled, 91 plus.
Oh, thank you. Yes. Yep. Thank you very much. Okay. So then when we add them all back up, this gives us the individual firms Q. Big Q is going to be n times Q star. Which is going to be n over n plus 1 times 100 minus t. So if n is very large, the left-hand side of that is going to be approximately 1. Yeah.
We always.
Yeah, there probably is a way to do that. There is probably a smarter way to do that. This is the way that I've been thinking about it in terms of the individual firms, but yes, absolutely. A great way to study for this problem would be to figure out how to do it with big Q. So thinking about this last part here, we've got this market level Q star that happens when the firm is reacting to the tax, when each of these individual firms is reacting to tax. So if n is large, let's say it's going to infinity for the sake of it, like doing this exercise, then Q star would equal, well, let me say first, n over n plus 1 goes to 1, which implies that Q star will be 100 minus t. Yeah. You were saying, can you say that one? Marginal private cost, which plus the tax. And so the marginal private costs here would be, which is kind of what we have up here, right? The derivative of the total cost. Is our total cost function. Yeah, 2Q. So our marginal private cost plus tax. Because that's the demand curve, Q star. And then this is an excellent way to do it, much faster on an exam. Yeah, so they end up, if we look back at what I was finishing up, is this would imply a tax equals 50 would force Q star to equal 50, right? Your solution tells us that a tax of 50 would also imply that Q star, you could go either way. You could say that if Q star was 50, then the tax would have to equal 50. And so they both are the same process. Essentially, we're setting marginal private costs plus the tax equal to marginal private benefit. Their way is much shorter. So I think that's an excellent thing to do. So when I was listening to the recording, I think this is actually a nice way to set up the problem. If you want to look through the derivative version, that's up here. Okay, thank you for bringing that up. Okay, so before we move on though, are there any questions about this problem? Yeah. You're saying, let's see here, this is number 1. And you're saying set the, equal to
It's just market damages.
equal, sorry, why would you set it equal to 50?
It is the marginal damages essentially optimal quantity.
Oh, the socially, right, yes.
Yeah.
So the marginal damages are equal to 50 of the socially optimal quantity, yeah. And then the intuition is yes, that we want, oh, what's a highlight? That's the intuition behind this. In a perfectly competitive industry, when you're giving a tax, that's true, yes. I guess so if we were to ask you, like, show us why, then you would want to go through all the steps. The intuition is that, yeah, your tax always ends up being the marginal damages if there's no market power in the situation. So that's a good point, which is sort of the point of the thing on the left, is that you're setting the marginal private costs equal to the marginal social benefit. And this marginal social benefit in this case is also the reduced damages. So it ends up giving you the same thing. But that's a great way to think about the intuition, is that the marginal damages should be equal to the tax. And I mean, I think that seems like an acceptable answer on a question, to say, I know in this situation that the tax should equal marginal damages. I know the marginal damages at the socially optimal quantity are blank. Therefore, we should set the tax for this. I think that's very acceptable in this problem. I think you want to be careful about making sure you understand what the setup is and making sure it's perfectly competitive industry, because if you have market power, that's not going to be the answer. And just looking at the details of the question. But I think all three of these would be accepted. I think alternative 1 and alternative 2 are probably better on exam because they're quicker and you can get through the rest of the exam if you want to come back and add more math. Yeah, okay. And let's move on to the second problem, which is about intertemporal decision making. So I'll speed through this and I'll hand it over to Max. I'll speed through the first two. So the idea here is that we are trying to make a decision between keeping our current water heater or investing in a new water heater. So we want to know, does the benefit that accrues to us from switching to a new water heater outweigh the cost of purchasing the new water heater? So let's set up this problem. We know that our current water heater has energy usage of 25 MMBTU is million metric British thermal units. Yeah, so it's a measure of energy. So I'm going to say capital E, the energy usage, is equal to 25 BTU. We've got our natural gas price, PE, equal to $6 per MMBTU. We've got the alternative is a tankless water heater that reduces our energy usage by 30%. So that means I'm going to call this E current, EC. And E new, I guess. Which is going to be 25 times 30%. The question here is how much do we expect to save each year? Yeah. Oh, sorry. Thank you. 1 minus 30%. Thank you very much. And then another way, well, yeah, so let's just keep that. We want to know how much we're going to be saving each year. That's the question, because these energy calculations are how much energy your water heater uses each year. We are thinking of a 5-year timeline because we're thinking this tankless water heater is only going to last 5 years. We're just assuming that, versus our current water heater that's kind of old is also only going to last 5 years. So we're just going to assume we care about the next 5 years. And we're going to look at the energy savings we would get, because our question with this is, do we adopt or not? So we could look at the total energy usage of our current situation and our total energy usage of the alternative. Another way to think about it is, what's the difference between the two? So we know that our current energy usage is going to imply a cost, annual cost, equal to 25 times 6, which is equal to $150 per year. Because we've got our annual usage and our price. And we know that the total, the cost to purchase is equal to $200. Thanks to the administration, we've got some discounts. Okay, so then the question is, do we choose to adopt or not? So there's this version of using a net present value is, if the net present value is positive or negative, we can choose whether or not to adopt. So we're going to look at discounted. Of savings. So what this is saying is, if we look at the total value that we see now in how much we save versus the total cost that we're paying, that will be our net present value and help us make this decision. So the net discounted savings value is we're going to use this annuity formula that Meredith gave us in class from years 0 to 4. Yeah.
I just separately calculated.
Sorry, can you say that one more time?
I just separately, for without the year and the user, calculated the discounted costs. Those would still net present values.
You do it either way. Either calculate the discounted value of the difference.
Okay.
You would have the difference, you do that, and then you put the sum of that over, 1 point.
Okay.
Or to the, over time. You can do it that way. Or you can first discount the benefits and then discount the costs and take the difference of those. Those will be equivalent.
Mm-hmm.
This is we also
I'm trying to speed quickly towards that. Yeah. So what we'll want is some amount of savings, annual savings, over our 1 plus r to the t, and then minus our cost, which in this case is just going to be 200 because it's happening in the first year. So our annual savings is going to be equal to 30% times 150, which is going to be $45. So we can put $45 out front, do our summation from t to 0 to 4, 1 over 1 plus r to the t minus 200. And the hint in the problem tells us that's going to be 45 times 4.17 minus 200, which ends up giving us about negative 12. So in this problem, the net present value is negative, which means the benefits that we get from savings don't outweigh the upfront purchase. So we would not choose to do this in this case. The next part is essentially the same process, except it changes how much we save. The idea is that Governor Newsom is going to apply a tax, and the tax is going to, well, the tax is going to be at $20 per ton, which is going to imply, let's see here. The tax is going to be at $20 per ton. We know our emissions are about 1/20th of a ton of carbon dioxide per unit. So then those together imply that each MMBTU would cost us $1. Which means the new price is going to be the old price plus the tax, which is going to be $6 plus 1, which equals $7. So we can just go through the same calculation and look at what the new price is going to be. So we can still think about a 30% discount, but now the total energy savings is going to be more because we have a higher annual price. So that means our annual price, or annual cost, is going to go up to $175, which means our savings is going to equal 30% times 175, which is 52.5. So now we've got a higher annual savings. We can put that back into the same formula and say 52.5, 1 plus r to the t minus 200 equals about 1893. So now that we have this tax on carbon, it makes it more attractive to purchase this tankless heater. Yeah. So that is, we will accept both answers on the exam, but that is up to your discretion. It's kind of like, unless it specifies exactly in the problem, you can think of year 0 or year 1 as your first year of accruing costs. So another way to set up this problem would be to say, it kind of depends on when you're paying the upfront cost versus when you're paying your annual bill. In class, we went over an example where the summation was from like 1 to 5, and our cost was in year 0. That might say like, oh, at the beginning of the year in January, we're buying the tankless heater, but we don't pay our bill until the end of the year in December. So we're kind of discounting that a little bit. In this problem, or in this solution that I've written, is just assuming that we're paying the annual upfront cost and our bill at the same time, in both in year 0. And so that first amount of savings happens at the same time that we make the purchase, and then future ones don't. We'll accept either answer. But that's the reasoning behind it, is you can think of when the costs and the savings happen in time. Yeah.
So instead of Doing all the information like that, did you get the same answer to like those information, like you do it like the gas powering and not gas powering,
Yes, yes, because then you would end up being able to have all these same summation, these same sums. And that was the same question you were asking, I think, right? You'd have these same sums, but then the thing on top would be different in all of them. And so you could combine them all into something like this, where this is just the difference between them. This is the savings versus having them as different sums. So it's the same calculation, yeah. Yeah. Yes, if this were being asked on an exam, you could expect giving a hint, something like that. So I'm going to hand it over to Max for part C.
All right, so I'm gonna kind of speed through these last two parts here. Is there a microphone?
No, it's just right here.
Right here. Okay, cool. So I'm gonna speed through these last two parts so that we can talk a little bit about cap and trade programs. So we're gonna consider a third option here, part C. We're gonna receive a breaking news alert that Gavin Newsom has kind of canceled this this bill to have a carbon shortage bill. As an alternative, Sears is offering a financing option, which means so that you can purchase the product a little bit more cheaply up front. So instead of paying $200 up front, you can pay $100 up front and pay an additional $125 in 25 per year payments 3 years after the initial purchase with no interest. So basically, it's a little bit cheaper up front, and you pay a little bit more over time down the line. So how would this affect the net present value of the investment? Well, one part of the equation is going to be exactly the same. The savings will be no different from what they were originally. So we'll have NPV is once again PDV, I'll write PDV savings minus PDV costs. The savings are once again going to be T equals the sum of T equals 0 to 4 of the savings we get. So like 45 over 1 plus R to the T. The difference now is that instead of losing $200 up front, we're going to only lose $100 up front. So I'll swap out that 200 for a 100. But now we have to pay back and we'll pay back the remainder in $25 installments. So each period will pay $25. We'll discount the value of that like this. And because we need to pay back $125 in total, we'll have to make payments in periods T equals 3 through 7. So that will have to pay 25 each, and over those periods, then we'll pay back $125 in total. So what can we do next? Well, we can kind of bring this 25 here out front. Bring this 25 out front, and then use the hint in the equation, which tells us that the sum of T equals 3, sorry, the sum of 1 over 1 to the 0.1 to the T from period T equals 3 to T equals 7 equals 3.3. And then we'll just get the sum of T equals 0 to 4 of 45. Oh, sorry, we'll kind of, is there a way to erase easily?
Yeah, the erasers on the back.
Oh, cool. Wow. Okay, cool. Okay, I'll just kind of carry over the first part that we had from the previous equations. So this will get us, we'll have like 187.65 over here. I'll just subtract this 100 because there's nothing fancy going on with summation there. And we'll multiply that by, we'll subtract from that 25, which is the 25 over there, times, 3.13. If you kind of work through all of that, you'll get 9.4. So the idea is this financing option can make the net present value positive. Basically, why is this? It's kind of delaying some of the costs. It can be kind of hard to spend the entire $200 up front. And even if you kind of make the good a little bit more expensive, but spread that expense out over a larger period of time, that can make the investment more attractive to the consumer. All right, we only have a little bit of time, so I'm gonna, I'll scoot through question D real quick. D is you decide to buy the tankless water heater. How might this change the length of your showers? Discuss how this affects how you value this energy efficiency investment. So does anyone have any ideas about this one? Actually, we talked a little bit about this in class. Yeah. Yeah, what do we call that? There's like a name for that effect. Yeah, anyone have the idea? The rebound effect. Yeah, and it's kind of the surprise. Like you think like, oh, we'll make, their appliance more efficient. Well, then they'll use kind of like less energy overall. Well, it's kind of hard to know whether that's the case. Basically, you can think of this as happening two ways. Once energy efficiency goes up, the amount of income you have, the kind of like your relative income also goes up in a certain sense. You have more money to spend now that you don't have to spend quite as much money to satisfy your original heating needs. And so as the good gets cheaper, you might actually start purchasing more electricity over time. Sorry, and that's what the case would be with like the electricity situation. In the case of showers, you can think of it as a similar situation. You might end up taking longer showers once you have an energy efficient water heater. Okay, I'm going to skip through a little bit of the stuff there just because we have a lot to go through for the permits and taxation question. So I'll talk through that one next. So for this question, we're going to suppose that there's two firms, firm A and firm B, and they have a production process which produces pollution. They have different marginal abatement curves and different current levels of pollution. So currently firm A emits 20 tons of pollution. 20 tons of pollution. And they have a marginal abatement curve, which looks like MC of A. I'll put a little A down here so we know that's the marginal abatement curve of firm A is 2A. Likewise for firm B, we know that they currently emit 45 tons of pollution. And that they have a marginal abatement curve, which is just A. So what we're going to want to do first is we're going to graph on two separate graphs, firm A and firm B's marginal abatement cost, in which the horizontal axis is emissions. So the key thing to notice here is that we've been given these marginal abatement curves as a function of A, but we instead want to make them as a function of E so that we can kind of graph them a little bit more simply. So how are we going to do that? Well, we need some equation which helps us go from emissions to abatement. And that equation is not going to be particularly complicated. For firm A, they currently emit 20 emissions. So basically, we can think of E for firm A is just going to be 20 minus however much they abate. Does that make sense intuitively? Okay, so that's what it's going to be for firm A. So we can plug, we can solve this here for A, and we'll just get A equals 20 minus E. We can then plug this into their marginal abatement curve up top to get that MC of A, now as a function of E, which is what we wanted, is going to be 40 minus 2E. So if we want to graph this, we can imagine we have like E over here, we have the marginal costs up here. It's going to start at some point 40, and there's going to be like this downward slope of negative 2E. And so it'll hit the MCA over here, and it will hit the x-axis at the point 20. So that's what we have for firm A. Let's think about what this would look like for firm B. So firm B, they're currently emitting 45 tons of pollution. So their emissions are just going to be 45 minus whatever they abate. We can rearrange that to get A equals 45 minus E, and then plug that into their marginal abatement curve, which is just MCB of A equals A. So then we'll get, for firm 2, MC of B
as a function of E is going to equal 45 minus E. So theirs will kind of be similar to this, except it's going to start a little steeper. Maybe up here at 45, and then come down a little more flat than that. Then just a slope of negative E. So that will hit the x-axis at the point 45. So this is MCB. Is everyone clear on how I set those up for both firms? Okay. I think I'm probably only gonna have time to talk about question B, so I'll just kind of talk about that one for now. So let's suppose the government wants to cap emissions at E equals 20, and the government has decided to give each firm permits to create up to 10 tons of emissions. 10 tons of emissions. The permits are not tradable. So we want to graph the two firms' marginal abatement costs on one plot. And we want the horizontal axis to be the amount of emissions for firm A, which is going to be EA. So then we want to find out what each firm's abatement cost is. So we already know how to, write marginal abatement costs for firm A as a function of E. I'll kind of put EA down here. We've already done that. But we haven't done that for firm B yet. So let's spend a little time thinking about how we do that for firm B. Well, we know that in total, the emissions of both firms are going to be capped at 20. So if we do E sub A, that'll be the emissions for firm A, plus E sub B. That will sum to 20. We can just rearrange this to solve for what E sub B is. E sub B is just going to be 20 minus E sub A over there. So we know from before that the marginal costs of abatement of firm B are basically as a function of, actually I'll leave the function part away for now. So these were originally, 45 minus E sub B. We want to get this in terms of E sub A, however, so we'll take this E sub B over there and plug it in over there. And that'll then give us, this is going to be equal to 45 minus 20 plus EA, which is of course the same as 25 plus EA. So we can now graph these on a plot. Let's see, we've got 2 minutes to go. I'll just kind of talk about the last few things here that we'd want to think about at a high level, just so you have the basic idea. So this is going to be the marginal abatement cost curve for firm B as a function of EA. It's going to start at some point 25 and then kind of come up like that. For firm, that's for firm B. For firm A, it's going to start at some point 40 and then kind of come down like so. MCA. If we cap, if we mandate that each firm can't trade any of their emissions allowances, this will be kind of the allocation. And an important thing to notice here is that the marginal abatement costs are not equal here. So if both firms are emitting 10 and we don't allow for any trade to occur, the marginal abatement costs for firm B are going to be higher than those for firm A. So what would firm B want to do? Instead of abating, they would like to, if they were allowed to trade, buy permits. Yeah, you can basically do two things. You can either abate or buy permits. Those are your two options in sort of like a cap and trade market. If abatement is really expensive for you, you're going to want to buy permits from people who have cheaper levels of abatement. So in this situation here, firm A has cheaper abatement, so it would rather go for the abatement option and sell its permits. For firm B, the opposite situation is true. They would rather buy the permits and abate less. So two last things to figure out, like if you had a market, what would happen? Well, first off, the amount of emissions for firm A would be this point here, the point at which the two marginal abatement curves are equal. And the permit price would equal the marginal abatement cost at the point at which those two things are equal. So I'll maybe write this as like EA star. And you can think of the price in a cap and trade market is just going to equal the marginal, I should write this as like MA probably. Well, MC, every time I've written MC, you can think of it as MA, marginal abatement. the price of a permit is going to equal the marginal abatement cost of either firm A or firm B. They'll be the same at this point at the value E star A. Do we keep going or do you think? In the class here, okay. Okay,
The solutions, there are more follow-up solutions also in the practice problems solution. So these last two, intertemporal and this emissions trading one, are inside the practice problem solution. So you can look at those solutions for this one. The first one with just like the externality one that I went over is not in the solution list. But I'll post this recording as quickly as I can, kind of finish this process.
yeah,
And it's, again, the point where they both people, they're not.
right. So Ken, this is like if the government says, hey, you both, let's see. The government wants to cap emissions at 20 and has decided to give each firm permits to create 10 tons of emissions. So this is a situation in which the government says, hey, both of you are allowed to emit 10. And the important thing to notice here is the marginal abatement costs will not be equal at that point. So they would rather trade to get to another point, which I call a star, where those marginal abatement costs are equal.
Thank you all for coming. My office hours are today 2 to 4 upstairs. And otherwise, see you in the exam tomorrow.
Thanks, everybody.
Please bring a calculator. Please bring a calculator.
Yeah.